focus on some skills that you already have, and because it will be valuable for your project. So it will be not challenging. It will be like several little items during the meeting today. Okay. So I believe we have finished around this slide last time, maybe a little bit more in advance. And the goal of time-dependent density function theory is to get frequencies of transition at which resonance condition is matched, at which molecule is able to absorb light. And additional thing is to find the transition density or transition density matrix that corresponds to each specific excitation. In the density functional theory, this transition density matrices are stored as vectors, and they are referred as letters x and y for absorption and emission. Okay. So please, I'm skipping it now to go quicker over the material, but please remind me when it will be like closer to the end to speak a little bit more about projects. I will just check if you have questions and bring in some comments so that everyone feels comfortable. So on the left panel, we do have the list of concepts that I will cover in the today and coming lectures. So the goal for our consideration is to get the so-called Cassidy equation, which answers if implemented in a code at which frequencies molecule absorb light. This account of additional electron and electron hole interaction. So it is quite precise, agrees well with experiment, and respected in the community. So the project that Vola decided to do for the class may not go as far as this equation, but for the project that Vola is doing for the rotation, is Professor Kirina, I will guarantee that you will practice running TDDFT and being practically acquainted with Cassidy equation. And this will be done maybe in a week from now. So we have 3 lectures, including today on academic material, and then we will focus on the project in the last week. And the word trace that we expect to cover in a week from now will deal with the following thing. In order to predict intensities of absorption, one does need the oscillator strengths computed in a way which is more precise and more reliable than our present tools that we use in the project. So our present tools depend on orbital difference. So we are in the independent electron picture. Later on, after we cover this new theory, it will be oscillator strengths will be computed more precisely, and the oscillator strengths will be extracted from transition densities, from this rho EG, or from what is called x and y on the language of TDFT, x and y. And Cassidy equation will give us a set of frequencies at which molecule is absorbing. So this is the plan. And I just want to play open cards so that you know what are the goals. And on the way to this equation, and most largest amount of material will be related to this equation. It will take lecture or two. But in order to be on the same page, in order that you feel comfortable with this equation, which is quite okay, disconnected. I hope she'll reconnect back. Or maybe the material is so boring. I need to check this with her, and maybe in a few minutes I'll start a discussion which makes the meeting more vivid rather than me mumbling something boring. So I'm going to stop sharing in order to check if. Okay, yes, Kay is typing that she will restart laptop and join back shortly. Okay, before we get to the details of time-dependent perturbation theory, I want to bring in or review some background concepts that will be used as evident basis while talking about TDFT. And these basic concepts that I will try to start covering today will, so some of them you are acquainted with, and some of them I hope you're acquainted, but if you're not, I will be very happy to bring it in. So this is famous stuff. And I hope very much that the discussion today will be useful for your project. So, Kia, thank you for connecting back. You do not need to reply. I saw that you were restarting the laptop. So, right now, I'm going to discuss two concepts, which are not TDDFT, but they are related from the point of view of analyzing materials. In the whole class, this is mostly interesting and applicable to LoA. So for the project that you have selected, it is something that even if you do not compute what I'm going to say in a minute, it will be very much applicable to your work on metal-organic emitting complexes. And if you just mention the stuff that we discussed right now among the people who study emission of metal-organic complexes, it will be very relevant. So it's just, even without calculation, it is an important intellectual tool, the logical instrument. So Frank Condon and Stokes shift. Okay. So let me invite you to discuss what you see on this image on the right. So maybe Lolo, if you like, you may start and just share your vision, what you see on the right, and we'll go further all together.
I'm not exactly sure what VA means. Yeah, the total energy, I guess.
Okay, and energy as function of what?
I don't know what VA. I have no idea what VA means.
So yeah, I'm listening.
Yeah, I said I don't know what the VA means.
Capital A for position of ions, the geometry. Make sense?
No.
No. So when we were in the first chapter of our class, we were considering how to optimize geometry, how to find the minimum of potential energy, right? So and here is the ground state potential energy surface. So how the potential energy depends on position.
Okay.
Okay.
Yeah.
Okay. Good. Now, in this ground state, would you please comment what are these little things that I'm highlighting right now with green, and which are labeled as nu equals 0, nu equals 1, nu equals 2. What are these little?
Looks like frequency.
What?
Looks like frequency.
Nu 0, 1, and 2, yes. But what are these green things?
It's oscillator strength.
No. Like if you do not know, yeah, Lena, you must know.
Okay, so it's indicating the energy, as the frequency is related to energy.
Yes, but what are those?
Yeah, it's the waves. So as we know, the wave behavior of the electron is, we can describe the wave by the wavelength. So it's now oscillating more for the frequency 2, for example, than frequency 0.
Okay, so I want to bring in a correction. So this axis is position of ions, of nuclei, of atoms, not electrons. Do you have any corrections to your statement?
Yeah, so the atoms should be vibrating.
Yes.
With respect to position. So this indicates how strong that it's vibrating. If it's like vibrate like more, it will get more frequency.
Okay. And now I know that we agreed that there will be no exams, but suppose that we have a little exam based on the first chapter of this lecture. Do you remember anything about Born-Oppenheimer approximation?
For me, I don't remember.
Anyone remembers? Kia, do you remember anything about Born-Oppenheimer approximation? Maybe next year I should have more exams. Kia? Oh, she types no. I don't know how to encourage you to check it, but my last resort is Sarah. Would you try to remind us something about Born-Oppenheimer approximation? Just which memories you have about this beautiful theory?
Oh, I don't remember also as well.
But maybe something. What were we doing in the first chapter?
We were talking about energy minimization according to the position of the ions.
Excellent. It's a good starting point. Now, so we were minimizing energy in respect to position of ions. So basically, we're exploring this curve and going from higher energy to lower energy, right?
Yes.
Okay. And in this procedure, we assume that our nuclei are point charges, right? So each nuclei has a certain coordinate.
Yeah.
But this was approximately on the lecture 5 or 6, what we did before. So we, you may remember the picture that looked this way, like two positive ions, two negative electrons, and there were arrows in each of them.
Yeah, we described their kinetic energy.
Yes. Okay. Now, if you have position of ions with upper case R, position of electrons with lower case R, and everything here is stored in molecular wave function, which depends on both positions of ions and positions of electrons, and both ions and electrons are quantized particles, right? Which was the main challenge, which was undoable for any computer. And then born Oppenheimer approximation is that one can factorize this. Okay, I saw you raised hand, and I'll just finish sentence and then you'll speak. So the wave function that is composed of nucleus and electron is factorized on product of nuclear wave function and electronic wave function. And then for the subject that Sarah was telling, we told that instead of using nuclear wave function, we consider each nuclei as point charge, and we can optimize geometry. Do you remember now?
Yes.
Okay. Okay. And okay, I'll tell one more sentence, and then you'll speak. So the image that I'm showing right now is this chi of R. So these little things are, let me clean these arrows and draw here. So this one is chi naught of R. This is, next one is chi 1 of R. Next is chi 2 of R. And if the potential looks like parabola, then these nuclear wave functions will be very similar to eigenstate of harmonic oscillator. Lena, do you remember this concept from your physics courses? Eigenstates of harmonic oscillator.
Yes.
Okay. Now
Yeah.
I want to listen to the question of Kea, and then we'll discuss further from this point. Yes, Kea, please speak.
No, it's not about the question. It's actually comments of this equation. It's in a board. When you suddenly ask, it's like that. We study this equations so many months ago, like 1 or 2 months. So it's a boron approximation. We also consider Hamiltonian Schrodinger equation, right?
Yes.
So in the Hamiltonian Schrodinger equation, we consider that one in the Schrodinger equation. That one was the time dependent, right?
Yes. Yes.
Okay.
Yeah. You remember things. Yes.
Yes.
Okay. So what is there a question, or you just make a comment?
Make a comment,
Okay.
not a question.
Okay. Yeah. Thank you.
Actually, I was thinking about that. Which
It's
one?
good.
Which
It's good.
one?
It's good.
Should-
So, Luna, would you like to comment a little bit more about harmonic oscillator eigenstates?
So, as I remember, we solved Schrödinger equation for harmonic oscillator, and it was related to the state of motion of the ions inside the solid crystal. So their motion or it's not really stable, so we can just describe it as a harmonic oscillator motion. This is what I remember.
Okay,
And
that's good. That's good. So,
the solution for that for the Schrödinger equation with this potential. It was
Yeah.
easy to get the solution.
okay, well, it's not the easiest solution. It's mathematical.
When I was doing that, it was easy because maybe we just tried the simplest cases.
Okay, so if the nucleus is considered as a classical particle, it's just oscillation. But if it is a quantized particle, it's probability distribution, this chi of R, or amplitude of probability. And this eigenfunctions look like one camel with one hump, camel with two humps, camel with three humps, right? So good. We discussed the S naught, ground state potential energy surface. PES, potential energy surface, which can be quantized. Now, if we practice photoexcitation, if the molecule is promoted to the state S1, singlet number one, which we approximately describe as electron being promoted from HOMO to LUMO. So let me invite Sarah to give a comment on that. So, Sarah, is your microphone on?
Yeah.
Okay, so please compare the potential energy surface corresponding to S naught, lower one, and the one corresponding to S1, the upper one, the one which is highlighted in this pinkish highlight. So just tell what you see.
I think again for the excited state, we have to do the energy minimization, a kind of geometry optimization to find the which geometry or position will give the minimum energy again.
Mm-hmm.
So yeah, so
Good. I think you told most important thing. Yes. So in the excited state, we can find the minimal position, right? Minimal energy. And how the position of minimal energy in ground and excited relate to each other. Just tell briefly what your expectation is. Are they do they need to be equal, or they may be different?
I think they are not necessarily should be the same.
Aha, excellent. And what Sarah told to all of us right now is the main principle of spectroscopy of molecules. So Sarah told that optimal geometry in the excited state is not equal to the optimal geometry of the ground state. And the potential energy surface in the excited state is not equal to the potential energy in ground state. So it's not simply promoting high in energy, it's also change the dependence of the energy on position. Make sense? And the eigenstate of the nuclear wave function, chi naught, chi 1, chi 3, will be a little bit different in the excited state. Okay. I thought it would be like 1 minute slide. Someone is typing. I will be back in 2 minutes. Yeah, I think he finds this lecture really boring. Yeah, it's, please come back whenever possible. Now, next question. I'll invite Lola to try answering it, and then we'll all discuss. So suppose we know potential energy surfaces of ground and excited state. Suppose the system is originally in the ground state of the in the equilibrium of the ground state, or in the lowest harmonic, lowest quantum state, in the lowest quantum state of the nuclear. So it's ground in sense of electronic state and ground in a sense of vibrational motion. So the question to the Lola is, please try to describe these 3 lines, blue, red, and green, and tell which of them corresponds to absorption of light.
The green line shows that the energy of the ground state, which doesn't change.
Okay.
You said absorption, right?
Yes, absorption.
The red line shows emission, I think.
Yes, perfect. Yes, you already answered the next question. Yes.
Then the blue line shows what's it called? From ground state to excited. I don't remember.
Absorption.
Absorption, yeah. So yeah, that one shows absorption.
Perfect. Yeah, thank you. You answered everything absolutely correct. So when we are practicing, when system is being excited by light, it happens so quickly that nuclei do not move. So the nuclear wave function of the ground state is immediately promoted from ground state to potential energy surface to excited state potential energy surface without change of the shape. And it happens at the same position where we have equilibrium geometry of the ground state, right? Makes sense. And then if system lives long enough in the excited state, then as Sarah did told to us, there is a optimization of the ground state, and system comes into the wave function that corresponds to this chi naught of the excited state. And it means it will arrive to a position that will correspond to minimum of excited state geometry. And then if the system decides, oh, okay, today I'm in a good mood to emit light, it will happen at different interatomic distance, and therefore it will practice different frequency. Okay, Kia, are you back? Probably not. Oh yes. Okay, then please answer. Does transition energy of absorption and transition energy of emission equal or different?
Could you please repeat the question again?
Transition energy of absorption and transition energy of emission, are they equal or different?
Absorption and emission. Transition energy. Obviously, that will be different.
Okay, which means the blue arrow and red arrow have different lengths.
Yes.
Okay. Very good. Very good. And now I'm going to bring in some consequences of this. So
Absorption and emission.
so here is an example of one of the experimental spectra, and right now I do not care which system it is, but it is some laser crystal, but for molecules it is the same. So for absorption, it happens on, well, it's typically more than one peak, but it's shifted more to the blue part of the spectrum. So absorption is more shifted to the blue. And emission is shifted to the red. Okay?
Yeah.
And the rationalization, the process behind this is that for absorption, the blue line takes larger energy, and for emission, it takes smaller energy, because upon excitation, there is a nuclear reorganization. The system travels to optimal geometry of the excited state.
Yes.
So when you are practicing Fermi, if you do optimization of geometry with Fermi key, then you can find this optimal geometry. So if your project relates to molecules that emit light, then practicing this Fermi optimization is really reasonable. Here I'm just trying to draw this absorption and emission by hand. So absorption is more blue, emission is more red, and frequency goes to bigger energy, and wavelength goes to smaller energy. And most experimental results are being shown in terms of the wavelengths, which is inverse of the energy. But if you look on the energy axis, then absorption has higher energy than emission. So, okay, this is a rationalization and encouragement to practice Fermi optimization. And among those who attend today, it is mostly relevant to LoRa. So if among your explorations of your molecule, you create another subdirectory, do Fermi excitation, and then make NSW big enough, something like at least 100, and just run it to optimize, you will be able to find the difference between absorption and emission frequencies, which one of it will be like a little discovery for your project. Okay, so we are done, and one more thing. I know instead of 5 minutes, we are talking for 35 on this subject. You see these discrete frequencies, and if nuclei are quantized, the transitions happen literally between resonant conditions, not only blue and red, but also green light from different vibronic states, so to say. And these transitions of when one, instead of absorption and emission, one gives exactly literal numbers of the harmonics in the ground and excited, is typically seen in the Raman scattering. Also, if one needs to find exact profile of absorption, there is a correction to the stuff we are doing here in the class. In the class, we consider only electronic transitions, right? But in reality, especially in soft molecules, there are vibronic transitions, where there are resonance conditions between different quantum states of nuclear nuclear motion. And these transitions that take into account this quantization of nuclear motion are called Frank-Condon theory or Frank-Condon factors. Let me write it. Frank. Oh, it is written here. Frank-Condon. So if you want to dedicate your life to spectroscopy of molecules, you may read about this subject or refresh your knowledge if you did it before. Okay, why it is needed on our way to Cassidy equation? Cassidy equation will not literally explore this, but we need to know the area about where we make our consideration and what we are going to neglect or take into account. And this is an important effect that we need to keep in mind if we describe realistic systems. Now, next subject, charge transfer in one dimension. This is very much related to Kea and her project, and it is more or less related to Lina and Sarah. So when we will be meeting in the lab on coming Wednesday, I will provide practical skills related to it, but now I'll briefly introduce some concepts and just as a seed of thought, so that later on you can relate to it. Okay. So by analyzing your models for the project, it is very much encouraged to compute and plot charge density, spin density, and orbitals. If you haven't done it, please consider doing it and including them into the report. Suppose we do have orbitals or just charge density. Yeah, here is something that I think it's related to.
Yeah, in the last lab you showed something like this.
Yeah. So I think this one is spin densities, spin up minus spin down. So why this such information, spatial distribution of charge density and orbitals is needed? What do we learn from it? So we can learn if there is a hybridization between different units of the model, if there is a chemical bond or just physics option. And we can also learn if the charge is localized on one unit or another one, if the charge is equivalently distributed over the whole molecule, or it is experiencing transfer from one unit to another one. Why charge transfer could be useful? Let me ask Lina.
Yes. So do you mean charge transfer? I couldn't understand exactly the question.
So suppose you are studying a model like metal, substrate, and molecule. So if by some reason you identify that the molecule is charged positively and surface is charged negatively, what does it mean?
Yeah, so if the substrate is negatively charged, so that means it can bind to the molecule with the positive charge. And
by Coulomb attraction, right?
Coulomb attraction, it's electrostatic.
Yes. So exploration of the charge distribution of the charge transfer is needed to check if there is a Coulomb attraction or Coulomb repulsion, if there is a electrostatic interaction.
Yes.
Okay, very good. Now, if you are meticulously draw like 100 orbitals, which you maybe do not need to do for the project, but if you want to do it for publication, you may explore like hundreds of orbitals. They look beautiful, but it's too much information and too much disk space to analyze 100 of these three-dimensional balloons, right? And there is a way to simplify the consideration. So the goal of the analysis of charge distribution, well, there are several benefits, but one of the goals is to check if there is an electrostatic attraction or repulsion between units of the system. And in order to do so, we practice analysis of orbitals. And in order to simplify analysis of orbitals, there is a trick that I want to introduce now, and we will practice on coming Wednesday lab. Maybe I can just quickly create a slide right as we speak. Insert picture, profile, desktop, picture, insert, duplicate slide. So if our interest is distribution of charge, right now there is more stuff on the molecule, which means it's negative, and less stuff on the substrate, which means it is positive. So one way would be to just integrate all charge density on the top side of the cell and all charge density in the bottom part of the cell. Another thing would be to take z-axis, which goes orthogonal to the surface, and look how the charge depends on z-axis. So where we have larger amount of charge, we will have bigger peaks. Where we have less charge, we have smaller peaks. Where we have no charge, we will have zero. Does it make sense? Okay, so such images that project three-dimensional charge distribution to one-dimensional charge distribution are helpful in processing large amount of data on the space distribution. So one can, there is a way to convert orbitals as a file in this one-dimensional distribution and analyze it in order to say something about Coulombic interaction. Make sense? Whew. Good. Any questions about this verbal presentation of the concept from Lola, Sarah, and Kea? Just start speaking or asking question, or just stay muted if you are okay with this. Okay, it looks like you don't have question. So the orbitals, electronic orbitals, which depend on x, y, and z, are taken as absolute square. And this absolute value square of orbital number I is density as function of I, and we call it the part charge file. RCHG. The number of the orbital, something like 100, period, OK. Do you recognize this notation? Okay.
Yes.
Okay,
Yep.
so this file is a function of three coordinates, x, y, and z. Therefore, it draws three-dimensional structures. And three-dimensional structures are beautiful, but they are a little bit complicated to repeat again and again many times. They will just use your disk space and take your personal time of drawing. Although some people like drawing orbitals really much. So what if we perform integration of this part charge function over x and y, but keep dependence on z? So if you do this partial integration of partial charge, then we will convert it from three variables, from three-dimensional function to one-dimensional function. Make sense? Kea, please ask questions because it will be very much related to your project. You will need to do it.
Right now I don't have any question.
Okay, so it seems.
So if I have any question, I will send you email.
Okay, but the procedure seems reasonable to you, right?
Yes. Yeah.
Okay.
I can relate with this
Yeah.
one, and you can.
Yeah, here are just some examples
Okay.
from classes in previous years. So it was some crystal with one orbital localized in one part, and it showed this integration is non-zero only in the lower part as function of z. And for another orbital, it's in the other part. So it shows that by going from one orbital to another one experiences charge transfer. So for Sarah and Lina, analysis is mostly important to discuss the adsorption energy, to perform such integration of the total charge density. For Kea, it would be really beneficial to analyze individual orbitals because in the co-doped polymer is a candidate for photovoltaics. And most key factor of the photovoltaic effect is charge transfer from one orbital to another one. Okay, and a little thing that we may not practice in the class, but I want to inform you. So if we integrate 3 times over all 3 variables, 3-dimensional integration, then we should get 1 because we speak about 1 alpha. But if you multiply the charge density here, I noticed you raised hand. I just finish a sentence and ask you. Multiplied by position and perform this integration, then it will give expectation value of position for a given orbital, which tells approximate average position of charge. Same like in center, like there is a center of mass in engineering and physics, and here it will be center of charge. And this will be even simpler to speak about transition from charge being localized in one position of space to another position of space. This is related to the Os-dipole, but procedure that we use for oscillator strengths and transition dipole. But in oscillator strengths, we look for transition dipoles, and here we look for static dipoles. The procedure for integration is stored in binary, and the name of the script is something like band integrate, because VASP calls orbitals bands, and we integrate it over x and y. So it is the skill that you probably the last skill that we learn in the class, and we will go over it in the coming lab. Kia, you raised hand. Please speak now.
I think you already answered the question. Okay, so I'm asking that this one we didn't use. Still now we didn't use this command. That's why.
Yes, because we were discussing models for your projects and for all projects, and time did expire. But there is time to do it on Wednesday. Okay.
So, suppose if I want to draw for each orbital, I need to use this command, right?
Yes. Or you can, if you have few orbitals, you can draw both three-dimensional and integrated. Sarah, do you have questions about this procedure of integrating of orbitals?
No, I'm good.
Do you have the draft of the paper by Amir in front of you?
I should download it. Yes, I can download it now. Yeah.
Can you bring it to? I'll make you a co-host. Can you share it?
Yeah, sure. Just give me a second.
Okay. So the co-host. So the procedure that we are going to do right now, that Sarah is going to share some draft manuscript submitted for publication from her group, and it will be another illustration of the skill I'm talking right now.
Okay, find it.
And yeah, okay, so let's scroll to the figures.
Yeah, this is
No, next, further. Keep going, keep going, keep going, keep going, keep going. Next, yeah, and now enlarge it for the whole screen so that we can focus, or maybe even only panel A.
the A.
Yeah, just make it bigger so that everyone's about this time. So can you describe what you see and how you interpret it?
Yeah, so okay, if we use that command, I can plot this kind of graph for individual direction like X, Y, and Z.
So in the top panel, you see this little blue clouds, right?
Yes, yeah.
So those blue clouds are three-dimensional orbitals.
Yeah.
Which are beautiful, but it's more artistic rather than quantitative.
Okay.
And what do you see on the lower panel?
In the lower planet, it shows the charge density of the each direction. Like there is Z direction. In a Z direction.
And what is the connection between top panel and bottom panel?
So it seems like that the the red line of the dot line, this one. So
yes. So the areas, the z-axis on top panel is aligned as x-axis, right? It's parallel to the
Z direction.
Yeah.
Z.
So the areas of space where the blue clouds in the top panel are maximal, where they belong to the larger volume, correspond to peaks in the lower panel. Do you see?
Professor, one question. Like, yeah, there is a peak. So if I go to the top position, follow the red line, then there, yes, that blue and another color, I forgot the color name. So those portions give the maximum value of the charge. That's why he just want to show that portion here.
Yes.
Right?
Yes.
So why he did he show for the x direction or only not only for y direction here? Sorry, z direction.
The reason for analysis in Amir's paper is to check that charge density is continuously non-zero at each point, which
Okay.
means it is continuously distributed along polymer and it allows conductivity.
Okay.
Okay.
So
But
my question is why he just shows in z direction? Why not x, y?
it's possible, and you can do it in your project. We'll talk maybe one-to-one, and I'll show
Yes,
this
yes, of course.
little detail. But in principle, I hope everyone is okay and understands this transition from three-dimensional to one-dimensional.
Yes, yeah.
Dr. I just have a maybe silly question. I don't know. So this in the top panel, it has this molecule, and how we choose the orbital? Is it the HOMO?
Well, I think we should ask Amir to, because he's the author, to send his paper to everyone in class if he doesn't mind, and it is explained. But I can briefly tell. He takes few representative orbitals, HOMO -1, HOMO, LUMO, LUMO +1, and A and B. What we are looking right now are HOMO -1 and HOMO, and the next one, which we do not see right now, C and D, they are LUMO and LUMO +1, and he explores their similarities and differences.
Okay, yeah, that makes sense now.
Okay.
Comparing transitions and giving the density of charge, and it's maximum at the red dots here.
Oxygen, because oxygens are more electronegative and they have more electrons around them.
Yes, yeah, that's nice. Thank you.
Okay. Yep. So, Sarah, if you don't have questions on this yourself, then you can stop sharing.
Sure.
Yeah, thank you. So time is almost expired, so I'll just check what is next, and we'll target towards finishing. So we did consider the charge transfer, and next thing are transition dipole oscillator strengths and Einstein coefficients, which I'll start, and then we will see how it goes. This should be quite familiar to all of you, as we were doing homework on this subject, several homeworks, and as it relates to oscillator dipole. Here is the system.
Yay, so cute. Hi.
What's the name of your cat?
His name is Mickey.
What?
Mickey, like Mickey Mouse.
Oh,
Hi,
okay.
Mickey Mouse. Oh no, not Mickey. Not Mouse. Mickey.
Mickey
Hi,
cat.
Mickey.
Yes.
Okay.
To the first. Yeah. Hello.
Hi, Mickey.
How old is he?
Maybe 13 years old.
Wow.
I think she want to sleep.
Maybe. So, with his assistant, we'll continue. He likes very much to step on the keyboard, which is
Yes.
not the best thing. Oh, he went out.
Mickey also want to be a professor, actually.
So, if we practice not static dipole on previous slide, but transition dipole, which is needed for absorption spectrum, then we also do three-dimensional integration over x, over y, and over z. And instead of the same orbital, instead of charge density, we have different orbitals, I and J, and we put position operator between them. So this equation basically explains what we do when you run the script, the code os dipole, which generates for you the os dipole, and I think it's like version 3 or whatever. So it takes orbitals from wave car, places between them position operator, and finds transition dipole for each pair of orbitals. So if for whom it is important, it is important for K absorption spectrum. It is definitely important for LoA. So for your project, transition dipole and spectra are most important observable. And for Sarah, it is possible, doable. It's maybe not the main thing, but maybe one can check because your the clay has some color, right? And you can identify what is the color of the clay model that you have. For Lina, this thing can be quite challenging because in the gold, one always needs several K points, and gold is not transparent. So
I wanted to check if I can do spectral absorption, but yeah,
you can try, but you will see a lot of absorption in a zero region because it is conductor. Gold is not transparent; it absorbs everything.
Yeah.
So as a result of oscillator os dipole, you get the three components of oscillator strength. So x, y, and z for each pair of orbitals. And if you do not like the equation in the red box, here is partial equation for x component, and there are similar for y and z. So one takes projection of coordinate and then makes an integration. No, it should be all three. And then after your components of transition dipole are available, you take lengths of this vector, which is multiplication of rho by column of the components, or you take x projection squared, y projection squared, z projection squared. So this transition dipole squared is the main component for the oscillator strength. And here is the equation that I was hiding from you for the whole semester, but now it is time to disclose it. So what is oscillator strength? So between two orbitals, I and j. So it is transition dipole squared and several factors. So the factors include mass of electron, charge of electron, the result of special average, because in real life your molecule can be arranged at any angle, Planck constant, and then frequency of transition. So all these things are included in the code, and when you are using oscillator strengths file, yeah, okay, it's good that you can see it. Then you practice absorption spectrum. When you will be writing reports, you put a methodology, you can copy this equation, but please do not do copy paste as an image. Please type it in Microsoft Editor, just by standards.
Yeah, yes, of course. There is several tools for the typing the mathematics in the what file. Mathematica, then what file they have equation.
Okay. Yes.
Math type.
Yes. And I will bring this concept today, but probably we'll repeat it next time. And if some of you need to depart, I understand. We all need to finish soon. So Einstein got famous because of several discoveries, and one of these key discoveries is so-called Einstein coefficients. I think Kea, Sarah, and Lina, no, Kea, Sarah, and Lola didn't have it in classes, may have it in the future, but I'm pretty sure that Lina saw it in her curriculum. So can you briefly say what are Einstein coefficients?
Okay. So I'm not really familiar with the equation.
No, just say about the image and maybe just tell by freestyle language. What they're about.
So what we know is the difference in energy between two states is related to the frequency of the oscillation, and that was done by Einstein when he just emitted light on the photoelectro. I just that depending on the frequency, it will be excited, not because of the intensity of the light. It was just depending on the energy of.
Okay. Not bad, but it is an absolutely correct answer, but to the different question.
Oh, really? What's the question again?
Oh, so you answered the question about the nature of photoelectric effect when electron is being driven out of material. And here Einstein coefficients deal about absorption and emission of light by a molecule. And a molecule here is approximated by two levels. So of course we know that each molecule, each material has a lot of levels. But we here we consider only HOMO and LUMO. And Einstein called it E1, E2. And then one assumes that, here I notice your hand, you will speak in a minute, that this system is being exposed to optical excitation, which is electric field oscillating with frequency omega. And the question that Einstein coefficient, the theory of this coefficient answers, what is the probability that due to this light, molecule will be excited from ground to excited? What is the probability if it is excited, it will come to the ground? And what is the probability that it will recombine without external perturbation? Kaya, please speak. I noticed your raised hand.
Yes. So my question, why for the A it shows the downward, because it's emission, okay, so it's downward, but in a B it also shows the downward and upward. So could you please explain this one briefly?
Yes.
Like I saw this kind of not in a details way, but I saw somewhere, maybe I don't know where I saw it, forgot.
Excellent. Your question is music for my ears. It's very relevant. I cannot formulate the question for this consideration better. So, what? And I am about to finish soon. We should. Thank you for staying longer. So, which processes can happen if the molecule is being irradiated by light? So the electron can go from HOMO orbital, from ground state to excited. And then it will be absorption. So letter A in the in what we will discuss sooner, it's the letter A doesn't mean absorption. It's not the most efficient namings, but since Einstein introduced it, people just follow what he designed. So A and B doesn't mean absorption and B something strange. He just tells process, like number one, process number two, process A, process B. So the B12 is absorption, and it is called stimulated absorption because it is stimulated by external light. So irradiated by laser or by sunlight, and electron is being molecule absorbs light, and there is a promotion from ground to excited.
Yes.
The probability of such transition is oscillator strength divided by dielectric constant and Planck constant. If we continue to irradiate the molecule after it has been excited, it will emit light back from ground to ground, and probability of this process will be the same. So this is probability of transition. So, and this is quite natural. Light induced absorption, and then light stimulates emission. But in addition to this stimulated processes, there is an additional opportunity. So what if we have excited molecule and switch the light off? Like you excite molecule and then bring it to the dark room, or switch off the laser. Will it stay in the excited state forever? Yes or no?
Yes.
No. And
No?
no. It is my favorite subject. I promise to finish very soon, but I
So we always thought that if it's in the excited state, it will go back to the ground state.
And Einstein thought opposite and got his Nobel Prize. And so the idea that excited state will live forever is the biggest lie of quantum mechanics. I'm not telling that people who teach quantum mechanics are lying, but in the closed academic course of quantum mechanics, when all systems are isolated, there is a postulate, right? That system brought to eigenstate will stay there forever. But it doesn't tell the truth that there are no isolated systems in the world. All systems are coupled to something. And due to this coupling, and specifically coupling to modes of electromagnetic radiation, which are everywhere, there will be so-called spontaneous emission. So the molecule brought to excited state will relax to ground state after some time with guarantee, for sure. The question is only how soon. And this answer, how soon, is called a lifetime of excited state. So lifetime of excited state is related to spontaneous emission. Spontaneous means there is no made up irradiation. It's just molecule is left alone and it emits. It relaxes, recombines back to ground state. So it's called spontaneous emission. And the probability of spontaneous emission is probability of induced emission times this combination of factors, including frequency and speed of light. So it's also probability. And if one divides by this probability and takes care of dimensionalities, it will give time units, which will be how long it will take for a molecule to relax. Note that in the Einstein coefficient, the transition dipole comes into nominator. If you look on 1 over Einstein coefficient, oscillator strength, which is transition dipole squared, comes into denominator. So lifetime is proportional to 1 over transition dipole squared, or 1 over oscillator strength. So the bigger oscillator strength, the shorter the lifetime. Okay, enough for today. Sorry for taking more of your time. Thank you for investing and your effort and staying. Everyone is welcome to disconnect. I'll stay just a couple of minutes if there are additional questions.
Thanks, Dr. Kellen. Have a nice weekend. Have a nice weekend.
Thank you.
Thank you, Dr. Klein. Have a good day.
You too, Sarah.
Bye.
Bye.